Hello and welcome back. Today I'll be looking at an example of a vector space, and the example that I will be looking at is a pretty popular one, and that's the Rn family. So Rn is basically a collection of n real numbers. It's an ordered collection of n real numbers. Each component in this array is a real number, and that's why there's the R, and since there are n of them, that's why there is the n. Now that's a pretty simple definition, and this is actually the vectors that you encounter in physics and computer science or engineering in general. The notion of addition is pretty simple for them. If you have two vectors x and y which have components x1 x2 all the way to xn and y1 y2 all the way to yn, the resultant addition of those also as addition of those also results in a vector, and it has components x1 plus y1 x2 plus y2 all the way to xn plus yn. So this is a component wise addition. Similarly, for scalar multiplication, there is x1 x2 all the way to xn, that's the x vector. There is a scalar, and the scalar belongs to the set of real numbers. Then a times x, or x times a, however you prefer to call it, is a times x1, a times x2 all the way to a times xn. This is also a vector, and this is component wise multiplication. And this sort of thing, anything from the Rn family, is actually called a real vector. If instead of Rn I had Cn, instead of all the components being from the set of real numbers, they were all complex vectors, complex numbers, then this would actually be called a complex vector. Alright. Now, is this a vector space? Well, we do call them vectors in physics, right? So, do they form a vector space? At least under these operations? If so, then over what field? Okay, the second question was actually not necessary. The answer to that is pretty obvious. They form a vector space over the field of reals, if they do form a vector space, that is. And that's what I'll be proving, or analyzing actually, if they form a vector space or not. The first property of closure is actually pretty simple to prove. X plus y is also a member of Rn. Why? Because x1 plus y1, x2 plus y2, all these components, since real numbers are closed under addition, each component will also be a member of the real numbers, and because of that, each vector addition of this form will also result in a vector that belongs to Rn. Similarly, since scalar multiplication also has individual real multiplications inside it, by the virtue of real numbers being closed under multiplication, this operation will also result in a vector that belongs to Rn. And hence, closure is actually pretty simple to prove in this case. But the point is, I have just invoked the closure of the field of real numbers, nothing else. Similarly, in commutativity as well, if I want to check the commutativity of addition, that's very simple. Each component here is x1 plus y1, x2 plus y2, something like that. You can swap the order of the operands in this as well. Why? Because real numbers are commutative when it comes to addition, and hence the real vectors will also be commutative due to that. They inherit from the field of real numbers. A times x and x times a are same. I have already mentioned that by definition. Okay, associativity is also inherited from that of real numbers, because x plus y plus z, it can be evaluated in any way. X plus y can be evaluated first and then z can be added, or y plus z can be evaluated first and then added to x. Again, same logic, you just have to find out whether component wise associativity is there, and obviously it will be there because real numbers are associative under addition. Even for multiplication, since real numbers are associative when it comes to multiplication, this rule will also be valid, and hence scalar multiplication is also associative in nature. Now until here we have seen that it all inherits from the corresponding property of the real numbers. Identity is something similar to that. So we use the additive identity of the real numbers, and each component is set to 0 from the real numbers. So the 0 vector looks something like this. And notice that it does satisfy the properties that an additive identity should. For any vector u, when added to 0, it will result in the same thing. So it inherits from the additive identity of R, component wise. Similarly, 1 times u is u. I mean, this is also simple to look at. So 1 is the multiplicative identity from the set of real numbers, and if you multiply that as a scalar with a vector u from Rn, it will result in the same thing. Now inverse, there is only one inverse in the case of vector spaces, and that is the additive inverse. So minus x, if you define it as the negative of x1, negative of x2, negative of xn all the way till there, then notice that if you add this to x, then it will result in the 0 vector. Okay, so you have constructed an additive inverse as well. That's also simple. This also inherits from the additive inverse from the real numbers. Now distributivity, again it also inherits from the distributivity of the real numbers. It's not that big of a thing. Okay, right, over here is something I have to erase. This stuff is wrong, but the rest of it is right. Okay, now there is a small relation between R and C. So if you look at R square, uh, the addition is a component wise addition, the multiplication is a component wise multiplication, scalar multiplication actually. For complex numbers though, it's defined as x plus jx2, but the addition, if you look at it, it also is like a component wise addition only. Just instead of writing it separately, we write the real part plus j times an imaginary part, nothing else. Sorry. The multiplication although is defined in a very weird way. So but this sort of multiplication is what exactly enables our complex numbers to be established as a field, while R square is stuck being a vector space. So if you look at this, the relation between C, the set of complex numbers, and the set of real numbers is that, and the set of R square, the real vectors, is that the multiplication over here, if you set any of the complex numbers to a real number, then it will be the same as a scalar multiplication only. So the complex multiplication is actually a much more general form of scalar multiplication. So you get scalar multiplication when you restrict one of the operands in complex multiplication to be a real number. Alright, that's the insight I wanted to provide you. With that, I'll end this video and I'll see you in the next one. Stay tuned.